Okay, so now that we have derived an equation for a right triangle intersection, we are going to derive the Muller-Tron-Bohr algorithm, which is right here. It's a more efficient version of this right triangle intersection. So it does exactly the same thing, just with less computation, so that this procedure can be done very quickly. So how do we actually get to this strange looking equation? Well, what we have from the previous question is an equation of the form mx equals b. This here is m, this is x, our unknown, and then this is b. So what should we do first? Well, let's look at hint number 1. So it tells us that we can express our equation in this form instead. So let's do that. So we have x equals 1 over the determinant of m. I'm just going to write out m for now, and we'll compute all of the determinants later. Okay, and then we have another matrix that's a little different than our original m. So first we take m and replace the first item with our b. So that'll give us, that'll give us this column, or this row, sorry. Okay, and then this is also a determinant, and then we have our row 2, which has its second item replaced by b. And then row 3 has its third item replaced by b. Okay, so now we have this other form of our original equation that involves a lot of determinants. In order to make this a little easier on ourselves, we're going to replace a lot of these variables here with the variables that we are using in our Muller-Tron-Bohr algorithm. So like these e's and s's, just so it's a little more compact. So let me just zoom out so you guys can see this. So we have x equals 1 over negative d, e1, e2, and then this is s, e1, e2, negative d, s, e2, negative d. Okay, so now that we have this, we need a little bit more room, so give me 1 second. Just gonna make this smaller. Okay, so now we need to actually compute these determinants. So for negative d, e1, e2, this is equal to negative minus d times e2 times e1. Okay, and then just to simplify this a little bit more, this is equal to s1 times e1. Then we have the first row of this matrix here, se1, e2. That's equal to negative e1 times s minus e2 equals s2 times e2. Again, we're just simplifying it a little bit here. I'm not going to go through the exact math for this here, but if you want to know more, please come to my office hours. Okay, And then this determinant, that's negative d times e2 times s, which is just s1 times s. And then the last one, the last row of this matrix is this. And then this simplifies to s2 dot d. Okay, so now that we've computed all these determinants, simplified it, we can just pop this back into this equation here, and this will give us exactly the Muller-Trimbour algorithm. So we have x equals 1 over s1 e, and then our matrix is right here. Okay, and let's just check ourselves. So yeah, it's exactly the same as the Muller-Trimbour algorithm here. So yeah, the main takeaway from this, I'd say, is that computation matters a lot. So simplifying your equation, your original equation here, into a more compact version can really speed up a lot of implementations. And you can kind of just use like these interesting tricks from linear algebra to get there. And you'll see this in like a lot of places, especially in ray tracing where every computation really counts.